Irregularity in ionization energy. This is today's lesson. In this lesson, we are going to learn what is the irregularity in ionization energy and what is the reason behind this. So, let's begin. Let us write elements that belong to period 2. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and finally neon. These are the elements that belong to period 2. Atomic number of lithium is 3, 4, 5 for boron, 6, 7, 8, 9, this is 10. We know from left to right along a period, ionization energy increases. This have been discussed in the previous lesson in detail. Nevertheless, let's try to recall the matter. Suppose this is lithium, which is a bit bigger in size, then atomic size decreases. Atomic size decreases from left to right. Then distance between outermost electron and the nucleus decreases. Distance between outermost shell electron and nucleus decreases, and when the distance decreases, then attraction force increases. When attraction force increases, removing electron from the outermost shell becomes tough. That means a high energy is required. That is, ionization energy becomes a high from left to right. From left to right, atomic size decreases, distance between outermost shell electron and nucleus decreases. As distance decreases, attraction between nucleus and outermost shell electron increases. Then, removing electron from the outermost shell, high energy is required. That is, from left to right, along a period, ionization energy increases. What is the irregularity? Let's see the matter. Here, beryllium. Ionization energy for beryllium is 899 kilojoule per mole, and boron belongs to the right side of beryllium. So, ionization energy of boron should be higher than beryllium, but this is actually lower than beryllium. Ionization energy of boron should be higher than beryllium, but actually ionization energy of beryllium is higher, that is 899 kilojoule per mole. On the other hand, ionization energy of boron is lower, which is 800 kilojoule per mole. This is the irregularity in ionization energy. Let's try to find the reason behind this. Here, electronic configuration of beryllium is, atomic number of beryllium is 4. 1s2, 2s2. This is outermost shell electronic configuration, which is stable electronic configuration. Orbital is fulfilled. 2s orbital is fulfilled. half-filled and full-filled orbitals are stable. Now let's see electronic configuration of boron. Boron, atomic number 5, 1s2, 2s2, 2p1. In the outermost shell of boron, 2s2, which is fulfilled, but 2p1, which is not half-filled, not fulfilled. This type of electronic configuration is unstable. On one hand, this is unstable electronic configuration. On the other hand, when this electron is removed, boron gets stable electronic configuration. So, removing this electron from 2p orbital is a bit easier. That is why ionization energy of beryllium is higher, 899 kilojoule per mole, because this is stable electronic configuration. But for boron, this electronic configuration is unstable, and after removing this electron, electronic configuration of boron becomes stable. So, to remove this electron, a bit lower energy is required. That is why ionization energy of boron is a bit lower, which is 800 kilojoule per mole. So, this is the irregularity in ionization energy, in which electronic configuration is responsible. Now let's see whether there is any irregularity in ionization energy. Now let's see about nitrogen and oxygen. Here, oxygen belongs to the right side of nitrogen. So, ionization energy of oxygen should be higher than nitrogen. Let's see the matter. Ionization energy of nitrogen, this is 1402 kilojoule per mole. On the other hand, ionization energy of oxygen is 1314 kilojoule per mole. Here we see that ionization energy of nitrogen is higher than oxygen. Actually, ionization energy of oxygen should be higher than nitrogen. This is the irregularity. Now let's see what is the reason behind this. Electronic configuration of nitrogen is 1s2, 2s2, 2p3. Here, 2p orbital is half-filled. Half-filled orbital is stable orbital. Now let's see electronic configuration of oxygen. 1s2, 2s2, 2p4. 2p4. This is not half-filled, not full-filled orbital. This electronic configuration is not stable. Let's see electronic configuration in the outermost shell in box method. Here 2p3. 1, 2, 3. Here 2p4. 1, 2, 3, 4. This is not symmetrical electronic configuration, but this one is symmetrical electronic configuration. This is half-filled, this is not half-filled, not full-filled, which is not stable configuration. Electronic configuration of oxygen is unstable. This is number one. Number two, from this unstable electronic configuration, when one electron is removed, then it becomes a stable electronic configuration. That is, after removing one electron, it becomes 2s2, 2p3, which is half-filled orbital. that is stable electronic configuration. So from this stable electronic configuration, removing one electron, it becomes tough. That is why higher energy is required, and this is 1402 kilojoule per mole. But for oxygen, the electronic configuration is unstable. Because of this, removing one electron is a bit easier, and to remove one electron from its outermost shell, it requires a bit lower energy, and this is 1314 kilojoule per mole, which is a bit lower than nitrogen. So again, here electronic configuration is responsible for the irregularity in ionization energy. This is all about irregularity in ionization energy. Ionization energy of boron should be higher than beryllium, but actually ionization energy of beryllium is higher than boron because of the stable electronic configuration. Again, ionization energy of oxygen should be higher than nitrogen, but actually ionization energy of nitrogen is higher than oxygen because of their electronic configuration. Stable electronic configuration, higher energy is required. In beryllium we see stable electronic configuration. That is why ionization energy of beryllium is higher than boron. Again, in nitrogen we see stable electronic configuration. That is why ionization energy of nitrogen is higher than oxygen. This is all about irregularity in ionization energy. No more today. Thank you very much.